Let's see how to build a model to convert text to an image. This code defines and initializes a simple text encoder using a recurrent neural network RNN with gated recurrent units GRU. The text encoder transforms text input into a numerical representation, which is embedding, that can be used for further tasks such as generating images from text. Let me break down this code step by step. First, importing required libraries. PyTorch library for deep learning and neural network models like RNN. Torch.optim is for optimization functions, and Torch Vision is PyTorch's image processing library, and Matplot library for plotting results. Next, defining the text encoder class. Text encoder function inherits from PyTorch NN model, meaning it's a custom neural network layer. Next, vocabulary size, which is nothing but number of unique words in our vocabulary. Embed_dim, the size of each word's numerical representation, which is nothing but 128 here. Then hidden_dim, which is the number of hidden neurons in the GRU. For example, 256. Next, creating an embedding layer, nn.embeddings, which has vocabulary size and embedding dimension. It converts each word integer index into a dense numerical vector, which is embedding. Example, if cat is in index 42, it maps 42, which gives 0.1 minus 0.3, 0.8 till it goes till 0.5. Adding a recurrent neural network GRU, which is nn.gru, it takes word embeddings as input and process sequence of words. The final hidden state acts as a compact representation of the input text. Then fully connected linear layer. It applies a transformation to the GRU's final output to refine the encoding. Next is forward pass on how text is processed. On step 1, converting input text into embeddings. Then processing embeddings using the GRU to extract meaningful information. At last, using the final GRU state as the text embedding, numerical representation of input text. So now initializing the model. Create a text encoder instance with a vocabulary of 1000 words. As I already said, word embeddings of size 128 and hidden layer of size 256. Next, defining the image generator class. It inherits from neural network module, which is the base class for all PyTorch neural networks. And input dimension, input_dim, defines the size of the random input vector. Example, hidden_dim is equal to 256. Next, defining the model layers. This is a fully connected neural network. It's not CNN yet. The model progressively increasing the number of neurons, transforming the inputs into an image. So activation function, we are using ReLU and TANH. ReLU is for nonlinearity and TANH used in the final layer to scale pixel values between -1 and 1. Common for image generation. Final output layer, which is of 784 neurons. Each neuron corresponds to a pixel in the generated image. So forward pass takes a random input vector, process it through the fully connected layers, reshapes the output from -1 to +1, and 28 into 28 reshapes into an image format. Initializing the generator uses hidden dimension of 256 This means the image generator is connected to the text encoder, where the text representation is used as an input. Here I'm defining a loss function and optimizer, which is MSE loss, measures how close the generated image are to real ones, and Adam optimizer updates the weights of both the text encoder and image generator. List of text underscore encoder dot parameters plus list of generator dot parameters ensures both models are trained together. Here I'm creating a dummy data set with a random samples of 100, and it helps me to create a dummy real image. Then I'm giving a training loop. It trains for 100 epochs. Optimizer dot zero underscore grad clears previous gradients before each step. Forward pass actually generates images from text. After finishing the entire training process, you can see the noise generated in this image. Now let me load the minutes data set, which contains handwritten digit images and assigns text description to each image based on its label 0 to 9. Here I'm defining a transformation for the image. ToTensor function converts images to PyTorch tensors and normalize 0.5, 0.5 normalizes the pixel value to -1, 1 for better model performance. Then I'm loading the minutes data set. Here I'm defining the labels to text description, creates a dictionary that maps numbers from 0 to 9 to their text representation. Next, it iterates through the data set and converts each digit label into text. Then I'm printing the text label of the first image, which is 3. Next, I'm defining the text to image dataset class, image underscore dataset. It has text labels and vocabularies, which is a dictionary mapping words to indices, which is nothing but a text encoding. Next, converting text into a tensor, splitting the text into words and converts them into a numerical indexes. If the text is shorter than 10 words, it adds padding to ensure uniform size. Next, I'm returning the total number of samples and also retrieving the image and its corresponding text sensor. Next, I'm converting all words used in descriptions into a dictionary mapping used in indices. After data loading as a batch and printing those samples, you can see the data fetches a batch of text image pairs. So now I'm going to train the model as I did previously. The generator feeds the text embeddings into the image generator, which is a CNN model, produces a 28 into 28 grayscale image from the text description, and I'm calculating the loss using MSC. So I'm just trying to give 10 epochs for each iteration. Now let's see how it is actually converting. Now I'm asking the model to generate 5. So let's see. Now we can see we have a image of 5, and I'm giving few more words 0, 3 and 7 just to check the performance of other digits. So we can see the image of 0, 3 and 7. Likewise, there are other open source data sets are available with labels. We can use that for training and generate text to image. So that's all for today. Thanks for watching.